Hello and welcome back to my channel. In today's video, I'm going through exercise 2.4 from the Art of Electronics. And in this exercise, we are looking at a emitter follower circuit and doing analysis for input and output impedances. So the question is saying that we need to show that the preceding relationship is correct. So that is this relationship over here, that Z out is equal to Z source divided by beta plus 1. And then it gives us a hint on how we should analyze this circuit, and a analysis for input impedance was done earlier in the chapter. So the circuit that we're looking at is this one over here, and this circuit is called the emitter follower. Basically what this means is that any voltage you have here appears on the output minus the VB voltage drop. So let's say you have 1 volt here, you will get 0.3 volts over here. So that may not seem very useful at the moment, but what it does is reduces the output impedance of whatever's driving this source. So let's say this is coming from a high impedance source. The emitter follower will reduce the impedance of that source so that the signal is not affecting it if it's driving something with a higher load. So let's first of all start with talking about what we know about this circuit. So if you know your BJT circuits, you know that the collector current, so that's the current going down this node over here, is equal to the current going into the base times the beta. The beta value typically is 100, but it does vary from transistor to transistor. The emitter current, the emitter of the BJT is this one over here, is equal to the collector current plus the base current, which is coming from this direction. So you have the collector current going down here, and you have the base current going this way. So the emitter current is basically a total of the collector current plus the base current. Next thing we know is that VE is equal to VB minus roughly 0.6 volts, sometimes 0.7 volts. It's not too important, but there is a slight voltage drop from base to the emitter. From the circuit on the screen, we can also deduce that the emitter current is equal to V out divided by Z out. So the output impedance is this one over here. Also from the circuit, we can calculate what IB is. So IB, which is the current going into the base, is equal to Vn, which is the voltage that's coming into the circuit, minus the base voltage divided by the base resistor. So that's basically Ohm's law. So we've calculated the voltage drop across the resistor, which gives us the current flowing in this direction. So we're going to use some of these to calculate our solution. So we know that the IE is equal to the collector current plus the base current. So if we had a small change in IE, which is basically denoted by delta over here, then that is equal to a small change in the collector current plus the small change in the base current. So what we're going to do is try to figure out each of these variables over here individually. So first of all, let's start with IE, which is a little bit easier. So delta IE, or a small change in emitter current, is equal to a small change in the output voltage divided by the fixed value resistor. Now let's figure out delta IB. So as we discussed before, IB is equal to Vn minus VB, which is the voltage at the base, divided by the resistor that's over here. Now if we assume a fixed voltage, we basically get rid of our constants because we're looking at deltas. So Vin is a constant because we fixed it, and Zin is a constant because it's a fixed value component. Therefore, Vin divided by Zin would also be a constant, so that's disappearing. And then we get left with VB over Zin. And we're looking at deltas, so we're just looking at a change in the voltage and not absolute values. Now VE is equal to VB minus 0.6. And if we look at the deltas again, the 0.6 doesn't change. So we can basically remove that from the equation. So we get delta VE is equal to delta VB, which we are also denoting as V out. So VE and V out is the same terminology, as that's the voltage on the emitter of the BJT. So we get delta VB is approximately equal to delta V out. Let's just call it it's equal to, as this 0.6 volts is a constant. So now if you're looking back at delta IB equals delta VB divided by Zn, we can replace the delta VB with V out, and this becomes useful later on to simplify the equation. So we get delta IB is equal to delta V out divided by Zin. Now finally, let's find delta IC. So delta IC is equal to beta, which is So delta IC is equal to beta times delta IB. So small change in collector current is equal to beta times small change in base current, which makes sense. Delta IB is equal to delta VB over Zin, which we worked out before. And we also worked out that delta VB is equal to delta V out. So we replace the VB with V out, and we get IC is equal to beta, and then we substitute this equation in. So beta multiplied by V out divided by Z in, and that basically gives us our IE, IC, and IB. So now if we substitute those equations into this equation number 4 that I've denoted here, so delta V out divided by Z out is equal to beta times delta V out divided by Z in plus delta V out divided by Z in. Now if we divide both sides of the equation by delta V out, we end up with this equation over here. So 1 over Z out, so this obviously goes to 1, and both of these also go to 1. And if we simplify this out, we get beta plus 1 divided by Z in on this side, and we get 1 over Z out on this side. Now to get to the equation that the question has asked us, we basically need to get to Z out, not 1 over Z out. So if we rearrange the equation, we get Z out is equal to Z in divided by beta plus 1. So that is a solution to this question. I would definitely recommend reading up on hybrid pi models for BJTs or small signal models of BJTs, as this will be very useful for understanding what's going on when the question is asking us to work this out. Now I've went through the method of doing it the way the book did it for the input impedance. However, I think it's more suitable to do it using the hybrid pi model. So I will make a video on this later on, but I don't need to cover this for the intention of this question. I think what they're hinting at is to use basic model that they've pointed to in the question. So that's what I've done. There are a ton of videos on YouTube for small signal models of BJTs. So in the meantime, you can definitely check them out. So thank you for watching today. Hopefully you like the content. Don't forget to like, comment, and subscribe. And if you have any suggestions for me, please let me know in the comment section below. Thank you for watching. Bye for now.